Please move up. There are seats in the front row and in the second and third row. So those of you who are standing in the back, please move up. Our next paper is given by titled Zeolite-based catalyst for extinction hydrocracking, and it is authored and presented by Dr. T.Y. Yen, Mobile R&D Corporation. Dr. Yen.
Zeolite-based catalysts are widely used in processing processes. We have studied and improved zeolite-based catalysts for extinction hydrocracking. Today, I wish to share with you some of our results, particularly our idea on the catalyst design. So my title is the Modified Zeolite-based Catalyst for Effective Extinction Hydrocracking. Hydrocracking can be carried out in one or two-stage process. In two-stage process, we can improve its performance. That means higher selectivity and longer operation cycles. Here is a two-stage process. The fresh feed is treated in the first stage, and then cracked in the second stage reactor. The effluent is fractionated to get the overhead product, which is naphtha, and then unconverted product is recycled along with the fresh feed for cracking in the second stage. So the next process is total conversion of the feed to the naphtha product. Today I'm talking about the hydrocracking catalyst, which to be used in this second stage. It is highly desirable to use zeolite-based catalyst for hydrocracking purposes because it is active, selective, stable, and resistant to nitrogen compounds poisoning. One of the important characteristics of zeolites, which distinct from the amorphous catalyst, is its uniform and small pore size. At the 4 to 10 Armstrong pore size, they are very close to the critical diameter of the compounds being cracked, thus leading to shape selectivity. They are very effective for cracking small compounds, but it's not very effective for large compounds. As a result, we found that the rare earth exchange impregnated with nickel, we call nickel tungsten REX, is not very effective for extinction hydrocracking. Similarly, Jan's Maxwell of shale oil also found that nickel tungsten on USY is not effective for extinction hydrocracking. Previously, we have reported that the zeolites and amorphous catalysts can be placed in the separate reactors to complement each other, leading to effective extinction hydrocracking. The objective of our study today is to develop a single zeolite-based catalyst for extinction hydrocracking. Our approach is to combine zeolite and amorphous-based catalyst into a single particle to form a composite catalyst. For this approach to be successful, the catalyst has to be able to, these two components has to be able to operate independent and complementary, and this at the same operating conditions. Indeed, it is a tall order, but luckily we have succeeded. The zeolite base is prepared by impregnating REX, rare earth exchange X, and the amorphous part is prepared by impregnating nickel tungsten on amorphous silica alumina. The composite catalyst was prepared by mixing these two components and extruded to form a single extrudate. The feedstock consists of coker gas oil, Catford gas oil, and fluoro extracts of wide boiling ranges. And this feedstock is then hydrotreated to a nitrogen level of 1 ppm for this study. The reaction system we use is a flow reactor with complete recycle. And the experiment was conducted for extended period of time so that we can assess the long-term performance of this catalyst. Our experiment shows that the zeolite amorphous composite catalyst was effective for extinction hydrocracking of feed with a wide boiling range. This assessment is based on the catalyst activity, stability, and its product selectivity as well as its product stability. In addition, we conclude that zeolite and amorphous components indeed operate independently and complementarily. Now let me show you some of our results which leads us to this conclusion. Here the activity of the catalyst is expressed by plotting the reactor temperature required to convert 60% per pass against the on-stream time. The catalyst was stabilized at somewhere around 580 degrees and aged at a quite low rate of about 0.2 degrees per day. In comparison, if it were pure zeolite, we were not really able to stabilize them because it aged too fast as reported previously. In comparison to amorphous catalysts, amorphous components rather, it was stabilized at about 610 degrees and aged at 0.6 degrees per day, 0.6 degrees per day, which was not shown in here. In order to see how those components work together, we analyze the feed, both fresh and recycled feed using chromatography to see how the conversion of these two components are. Now here is the fresh feed, and this is the recycled feed from amorphous components. I wish you to notice that when you do use amorphous catalyst, the heavy end was decreased and a much bigger spike. Incidentally, those spikes are paraffins, a signature of paraffins. If you can mentally remember these pictures, now I show you this. This is the recycled feed in the same kind of operation with pure zeolite alone. In compared to the amorphous catalyst, you see the heavy end is greatly increased. And with the big peak of bore head, no more spikes. Now this is the composite catalyst, which shows that the heavy end was decreased and in a way quite similar to the amorphous base catalyst, with only one small difference. You will see the paraffinic structure here is greatly diminished. Means that indeed the zeolite-based catalyst is working so as to crack those paraffins more so than amorphous catalyst step. And the result, this shows indeed the two components are working complementarily. Now here I show the product selectivity against the on-stream time. As you can see, over the extended period of 127 days, the product selectivity remained rather constant. And the naphtha selectivity is quite high at about 83% or so, with a very good quality for reform. This composite catalyst also is very resistant to nitrogen compared to amorphous catalyst. When the feed, the nitrogen content in the feed was increased from 1 to 12 ppm, the temperature required for this composite catalyst was 30 degrees, contrast to 90 degrees requirement for the amorphous components. And this catalyst, composite catalyst, is also fully regenerable by oxidative combustion. Here, the regenerative catalyst activity and the fresh catalyst activity were compared in this figure. Essentially, the activity was recovered. In addition, the product selectivity remained the same. One more. It's a summary slide. If you can. Oh, if you don't find, that's okay. Anyway, let me summarize what I have presented. The self-selectivity inherent to the zeolite catalyst can impair the application of zeolite catalyst in extinction hydrocracking. We have discovered that the zeolite and amorphous catalyst in a single particle can operate complementarily and independently. The resulting catalyst is superior to either of the components, and the composite catalyst is active, stable, selective for naphtha, and resistant to nitrogen poisoning, and completely regenerable. Thank you.
Thank you very much. And this paper is now open to questions. Yes.
Maxwell from Shell. Hi. I enjoyed your paper. I wondered if you've looked at the nitrogen resistance of the system at higher nitrogen levels. I noticed most of your recycled data was at 1 ppm nitrogen in single stage feed.
Right.
What's the highest level of nitrogen at which you operate the system?
The highest ever I had to try was about 30 ppm of nitrogen.
And you retain the function of the amorphous component at those higher levels under recycled conditions?
I wasn't able to directly compare because amorphous catalyst was not very good for comparison purposes. And the reason I used such a low nitrogen level was the time, because during that period of time, it's very fashionable to do a very low nitrogen compound and nitrogen level. You can see the age of the work.
Thank you.
One more question.
Nikolaitis, Rabakoan. You showed in your plot that your naphtha yields were approximately constant with time on stream. Was that actually true even though your reactor temperature was increasing?
Yes, sir, it is true. Because in the selectivity start to change badly at high temperatures than I terminated. It generally start to deteriorate very badly over 700 degrees F.
Thank you very much again.